So over here is the plant, the MATLAB code I shared with you as the plant transfer function. So it's over here. And this part over here is the PID controller. You can see KP, KI, and KD. And we use MATLAB to calculate these gains. All right. In MATLAB, it's just a single command. If you know the transfer function, right, you can generate the reasonably acceptable PID gains. And then we use these gains here in the Simulink. Now we have MATLAB M file and Simulink block working together. So when you run the MATLAB code I gave you, it's on the Moodle, you can download and run it. It launches the Simulink model, which is this one. Before you launch the Simulink model in MATLAB, you calculate these gains. So by the time you launch the Simulink model, the gains are available. Okay, the CS is the controller, PID controller. CS.kp is the proportional gain. CSKI, CSKD are integral and derivative gains. Now over here is the integral controller. You get the integration of the error, all right, and then send it to the gain. In this particular configuration, right, this integral control is full-time on. You can see that when the error is generated over here, it goes through the integral control because we have terminated the anti-wind up processing. All right. So in MATLAB, you can do that, right? In Simulink, you can connect this point to here directly without this jumper. Then the PID, actually I controller, is subjected to anti-wind up, right? Okay, so either way you can simulate the plant. The rest I explained you the other day, how we get the saturation detected, all right? When the control signal is saturated and at the same time, the control signal and the error have the same sign, right? We combine these two together. If that condition is satisfied, we turn off the integral controller temporarily. Okay, right. So please download those files and put it in one folder in your machine, run MATLAB, MATLAB code, then you will see the results. After that, you can change it a little bit here and there, right, to explore. So these are some of the results you get, right? So without anti-wind up, you will see this kind of overshoot, all right? This kind of overshoot. Ideal response is the blue one. What do I mean by ideal is that when the actuator does not saturate, actuator can produce any control signal that the PID controller is asking, okay? This is not ideal, not realistic, but this is actually ideal case, not realistic. The realistic one is when you have a limit for the actuator, then you will see the error goes like that, right? Control signal is not strong enough, cannot deliver the excessive control signal the control is asking. So therefore, it cannot control the error. So error increases like that, okay? So if you don't have anti-wind up, this is what's going to happen. Very interestingly, over here, you can see the PID control signals, right? P, I, and D. You can see the moment you change your reference, like over here, again over here, again over here, again over here. Every time you change the reference, right, you will see a lot of aggressive controls coming in from basically P and D controllers, P and D controllers, okay? But the I controller doesn't do much. It doesn't change much, right? But when you keep the reference unchanged for some time, right, the system settles down at that point or wherever it settles down. And at that moment, it's the I controller which has some significant value. Both proportional and derivative controllers, they go to sleep basically, right? It's a very interesting finding. And on the left-hand side, you can see the saturation signal. You can see the blue towers here, 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 and here. When the anti-wind up kicks in, it stops integral controller in this part, this part. So we don't have to worry. This is kind of done and dust. Once you do that, right, it will decide when the anti-wind up has to be activated. All right. Now, if you introduce a little bit of noise, how can I do that? In simulation, you can see it over here. This is a plant, okay, and the output. Now we add a little bit of noise here, okay. Now noise is everywhere, right? When you deal with physical systems, you capture your response or output with noise, and you feed it back like that. This is the noisy feedback, right? Noisy response that you feed back because you don't have any other option. You have to feed back your response. So when you do that, this is how signals are going to change. You can see the actual response actually is similar to what you saw earlier, but this time it's noisy. There's a bit of noise, right? And control signals, they're all the same, except the integral control, because integral control is integrator. When you have this kind of denoising process, right, it's much more smoother. But proportional and derivative terms, particularly derivative terms, right, you can see they are kind of very noisy. Because of noise, you get a lot of control signals generated by particularly the D controller, right? Therefore, many occasions, the control signal demand goes beyond the limits. So therefore, you can see here and there, a lot of anti-wind up kicks in here, here, and this is basically because of the noise. Quite unnecessary. Okay. Now, actual anti-wind up is actually only in these 4 places. Okay. But now because of noise, you have a lot of anti-wind up kicks in here and there, quite unnecessary. And this is what a noise can do to a system. All right. So now you have actual or simulated results, but that shows you very comprehensive information about controls. Okay, now you go deep into the control system and look at the signals and how it works. So now we understand the problem is noise. So let's deal with it. Right? This is the proper learning curve. Rather than having a set of topics and try to learn, we study the basic things. Okay, we want to do something. And when we get going, we we tumble, right? Because of various problems. And then when you try to solve this problem, right? So that is the best learning approach. So now we know that, okay, you have heard of noise even before this, but maybe this is one specific moment you saw its real nature in a control system, feedback system. Now you appreciate that, okay, we got to do something, right? So we naturally tend to start our next discussion, how to deal with noise. And when I say noise, what comes to everybody's mind is Kalman filter, because the Kalman filter is one of the greatest filters developed by uh, uh, Rudolf Kalman. I recommend you read some of these historical things, right? How he developed that, and when a NASA scientist came to know about this filter and how they got it to Apollo mission, how the Kalman filter was developed to extended Kalman filter by one of these engineers at NASA. Okay, so it's very interesting historical stories, science history. When you learn, please spare a little bit of time to read about the history, because that'll help you to place your knowledge pieces with respect to each other in a very nice continuum. Okay, right. Now, I have 3 points to tell you about noise and Kalman filter. Okay, I want to teach you specific things by numbers 1, 2, 3, and so on. So it's very easy for you to understand and remember. The number one thing is the true response, Y sub T, true response, okay? True response from the plant. Consists what is generated by the unmodeled system dynamics, all process noise. Now, as you know, you cannot model plants very precisely, because there's always something that you cannot model. Okay, so but when you operate a plant, all of these things are there and they generate the response. Okay, and that is why what I call as true response. True response. And this true response uh, has this unmodeled dynamics in it, right? And these unmodeled dynamics appear as something similar to noise. Something similar to noise. Okay, you model 95% of the system. The remaining whatever percentage, 5%, 3%, whatever, is kind of noise, somewhat similar to noise. If it is very visible thing, you would have modeled it in the first place. Okay, these are imperfections in the system, but we don't know about it. But when we get the result and compare it with our result, then you see there's some difference between the two, and this is coming from the unmodeled part of the dynamics. So for the moment, let's say that this unmodeled part produces some component in the plant, and we uh, uh, even though it is not very correct to say a noise, is very much a part of the response, something within the system, but let's call it process noise, because historically it has been termed like that. And it has a covariance Q. Covariance is, when a signal fluctuates, right, above and below a certain level, right, you get that variation, deviation, and you generate covariance. So if you have forgotten covariance, please just Google it and find it out how to calculate covariance of a signal. All right. Covariance is actually variance if the signal is the same signal. Okay. If you have two signals and try to find out the variances, we call it covariance. Number two, the sensor reading Y is different from the true response YT. When you put a sensor to read the response, because response cannot be read, cannot be seen without a sensor. Always you got to have a sensor to measure and look at it, right? So let's call the sensor reading as Y. The YT is not knowable, right? Unless you have a sensor. Once you put the sensor in, what you do is you have the sensor noise also. All right. Now, if you line up the blocks, you can understand, okay, you have the modeled part of the plant, and you have some response from that, and you have unmodeled dynamics of the plant, and there you have another component. You add them together, and that is YT. But when you put the sensor in to read the response, sensor has its own noise. All right. So the sensor reading is Y. All right. And sensor has its own noise, as I said, and that noise can be represented by mean and covariance again. All right. So when you read the response from the sensor, it is a noisy output. So if I go back to the plant, I can show here, right? When you read it from here, can you see the sensor noise comes in, and when you read, noise is already there, right? And within this block, there's no unmodeled dynamics because it's simulation, but in actual plant, there will be some process noise here, unmodeled dynamics. All right. Now, the Kalman filter uses the plant model, which is this one, plant model, right? But it uses plant model in what is called state space format, not the differential equation or the transfer function. Okay, so I'll teach you how you can get the state space model of the plant. The state space model has four items A, B, C, and D. So we'll discuss that next slide. And the Kalman filter also needs a control signal. What is the control signal you are giving to the plant? So if I go back few slides, I can tell you that this is the control signal. Okay, or rather here after saturation, this is the control signal. So Kalman filter needs to know before it can do anything, what is the model? Okay, what is the control signal? What else? It needs to know process noise covariance. This unmodeled dynamics, it needs to know something about it. Okay, this is a questionable thing. How do we know in the first place the unmodeled dynamic, right? We call it unmodeled because we cannot model it. So then how do I know it? There are ways to find that out. And also sensor reading. Let's go back. Where is the sensor reading? This is the sensor reading. After noise addition, sensor reading. So Kalman filter needs to know that as well. What else? And sensor noise covariance. We need to tell Kalman filter, okay, I have this sensor. This is the sensor noise covariance. All right. With all these things, Kalman filter has 5 equations. It will run the 5 equations recursively, right, and produces every loop what is called the best estimate of YT, the true response. This one, okay, with unmodeled dynamics included, right, the genuine response, okay, without the sensor noise. So that is the beauty of the Kalman filter. The mathematical derivation is there. If you are interested, you can look at it. It would be a bit lengthy, right? But eventually it boils down to just 5 equations, right? So what it does is that it takes all of this information and produces uh, the true response, right? Which is in our plant, this one over here, before you add the sensor to read it. Now, see how beautiful it is? This noise is basically coming from the sensor, and without the sensor, you cannot know it, right? Now, what you do is this Kalman filter comes in and estimates what the signal value over here is, right? Before you add the sensor. So now you have the option. You don't have to feed back the noisy response, but you can get the Kalman filter output, the true response estimate, and feedback that one. Because there's no point of feeding back sensor reading knowing that it has noise. So why should I feed back a noisy response? You got that point? We need to input something or feedback something, the response without sensor noise, right? We don't want to feed back sensor noise. That's why the Kalman filter estimates the true response over here before you add the sensor noise. Right. So I think in this course, I'm not going to teach you Kalman filter. By the way, this is the standard Kalman filter, not the extended Kalman filter. But in your projects later, you will use mostly extended Kalman filter, right? The difference between the two, I can tell you that the standard Kalman filter, this is for linear systems, which can be represented by transfer functions, right? But if you don't have a transfer function, but you have set of equations of your plant, and some equations are nonlinear, right? Then you can use the nonlinear version of this one, which is called the extended Kalman filter. In MATLAB, both options are available, right? All right, now the next problem we actually faced with is the Kalman filter needs what is called the state space model. Here, can you see that? State space model of the plant. So we want to generate the state space model. What we have is the transfer function. So next I'm going to show you simply how the state space model is generated from the plant dynamics. Now let me take this equation number 1, the differential equation. This is the plant model. Remember, this is the very first thing we did. When you try to model the plants, we end up having ordinary differential equations like this one, the system model. And then we use Laplace and generated the transfer function of this equation. Okay, now we know that we cannot continue with the transfer function to Kalman filter. So we go back, or we come back to the differential equation and try to generate the state space model from there. So when I generate the state space model, the first thing I need to do is to find out my dependent variable, that is y. I have y dot, y double dot. In this particular equation is a second order differential equation, second order system. And ut is the control input. All right, remember, in our shock absorber, it's a force. In our RC circuit, it's a voltage. Here is the abstract equation. We have ut as the control signal. B0, A0, this is A1, right? These are coefficients of the differential equation, and they are constants. Therefore, this equation 1 is a linear differential equation. That is why we were able to generate the transfer function. This is also a linear system model. Okay, so we are talking about linear systems. Now, the first thing I do to my differential equation is I go to the dependent variable yt and give it a name as x1. Okay, now y is x1. I replace y with x1 and I call it the first state variable. First state variable. And then I go to the y dot, right, to the left of that, and I replace y dot with x2t, and I call it my second state variable. Okay, so I declared two state variables. That is the first step, x1 and x2. What is x1? x1 is the response y. x2 is the rate of change of the response, y dot. Okay, and on the left, I have another derivative of the response, y double dot, but I don't assign another state variable to that. This is a second order system. I only need two state variables, x1 and x2. All right. Step 2 is to write down state equations. Now, if you have two state equations, variables here, state variables, x2 and x1, you obviously know that x2 is the first derivative of x1. right? X2 is the first derivative of x1. So you can write it like that. Actually, you write it the other way around. X1 dot is equal to x2. You write your rate of change on the left and the variable on the right. Okay. This is a second order system. So we have two state variables and we also need two state equations. We have got one. What is the second state equation? Well, it is actually the differential equation itself in state variable format. So you call the differential equation and you can see this one, second derivative of y, which is equal to the first derivative of x2, isn't it? If you get x2 and differentiate it, you get this one. So I replace dy y double dot with x2 dot. Okay. All right. When you go to the left, is the differentiation. Okay, by one step. So x2 dot is this term, and I take all the other terms to the right hand side. So I can write this equation. It's equal to minus a0 x1 minus a1 x2, and I have b0 ut anyway there. And that is the second state equation. I can write the two state equations in this arrangement. X1 dot equals x2, x2 dot equals minus a0 x1 minus a1 x2 plus b0 u. Okay. Now, what I have done in these two steps is that converting my second order differential equation into two first order equations. That is what the state space model is all about. In state space model, you don't have anything other than first derivative, right? You can see it over here, x1 dot, x2 dot. If it was a third order system, you will see x3 dot, right? But it's always just single dot. Depending on the order of the original system, you have that many number of equations, but they're all first order differential equations. So first order differential equation is very easy to solve. MATLAB really likes it to solve first order differential equations. Okay, right. Now I can put them into a nice format, matrix format, x1 dot, x2 dot on the left hand side, and on the right hand side you have these two equations getting arranged in this format. You have the system matrix and the drive matrix 0, b0, u. Clear? Any questions so far? Any questions, please? All right. So now we can write down this as x vector. There's a little error here. I think you can figure that out. So this should be x dot is equal to ax plus bu, right? So maybe I can correct that right away. All right. So now you see when you arrange the two state equations, they're all both first order, into a matrix format, you can simply write it down as x dot equals ax plus bu, right? This x is a vector, x1, x2, the two state variables in the system. Now the second part of the state space model is the output. Now, you have two state variables, x1 and x2. But if you go back to the differential equation, you will see your response is y. Okay, and y is actually x1 now. There's no y now because entire system is now represented by state variables, right? x1, x2, x3, and so on. So the response is actually x1. All right, so how do you get x1 out? Well, you have the state vector x1, x2. Then you multiply it with 1, 0. We call it output matrix, so vector, and that is y. Okay, y is equal to x1. But in general format, we write it like y equals cx plus du, where the c is this vector, right, 1, 0, and this is the state vector anyway, it's plus du. So you can say d is 0 here, right? Even if you bring u here, yeah, it's all 0, right? So in order to align with the generic format, you write y equals cx plus du, but most of the cases, d is 0. You only have y equals cx. Okay? Now you understand what these A, B, C, and D are. State space model of the plan. So if you know A, B, C, and D, right, you can tell MATLAB, this is my A, B, C, D. And then MATLAB understand your model. So when you use standard Kalman filter, you go to tell MATLAB what to A, B, C, D are. Okay. Now, how can we bring Kalman filter into the plant, right? So you must be really interested in knowing how you can do that, at least in MATLAB, right? In practical systems, it's much easier to do that. You have the Kalman filter, you just connect the response to the Kalman filter, okay? And you program it with your system dynamics anyway. And control signal also connect to the Kalman filter, and it gives out the response. But in simulation, you have to create this environment, so it's bit difficult. Actually, not difficult, just relatively. Now, let us do this conversion and work it out through an example. So we want to convert the transfer function y over u, right, to state space model. In fact, this is to go back, this one, all right, y over u. So this is a control signal as the input and y as the output. Okay, this is our transfer function. And to this format, x dot equals ax plus bu, yt, this is the true response of the plant, okay, cx plus du without the sensor. So please remember this sub t is the true response of the plant, okay, before you read it using a sensor. In MATLAB, it's very easy. This little code, few lines, will tell you how to do that in MATLAB. So you define your state space variable, Laplace variable s, and then define your transfer function gs, this one, okay? And then use num and then numerator denominator of the transfer function using tf data command in MATLAB. You can find those commands and the arguments, how it works and all that easily. And then launch this line ABCD is equal to TF to SS, transfer function to state space. So this is the command that you use to convert a transfer function to a state space model. And you give the numerator denominator as your arguments, and it gives you this result. I've taken it from my MATLAB. For this transfer function, Matrix A, system matrix is this one, dry matrix is this one, actually vector. C is this one, because this is a third order system, not a second order, third order system. It's like this. Uh, and D is 0, as I said earlier, right? So remember, this time the output is actually synthesized using two state variables, right? X2 and X3 over here, all right? So because it's a third order system, and also there's a 0 here, 1.5 times S plus 5. So there's a 0 here. Because of that 0, you get two state variables to synthesize together to produce the response. All right. So this is the transfer function, and this is the state space model of the same system. Now, when you use the Kalman filter in MATLAB, MATLAB has this Kalman filter block. You bring in that block to your Simulink, right? And as I said, you have to connect Y. This is Y, not YT, right? YT is the true response. That is over here, right? There's no way to know that, right? In this, only in the simulation you can do that. In really a realistic situation, there's no way to know that. Always it is after the sensor. So the Kalman filter is designed in that way, right? You have the sensor, and this is sensor noise, and that is fed back. It is interface to the Kalman filter. And the control signal, your control signal, you put that also to the Kalman filter. And inside the Kalman filter, you have this A, B, C, D already programmed into it. Okay. When you use the Kalman filter block, you have to double click and open. It opens and it asks you to enter A, B, C, and D. So you go ahead and input A, B, C, D. You define your A, B, C, D in your MATLAB code. And then in Kalman filter block, you just write A, B, C, D. Okay. Right. And then you can see it over here. This is a third order system. So it produces three states, right? And out of that, you get the third one over here, right? Using, yeah, here you can see x1 hat, x2 hat, and x3 hat. I use hat whenever the signal is estimate, okay? Somebody is estimating the signal. So that is what this hat means, right? X3 hat in this particular configuration is Y hat T. Okay, in this format, when you have the non-zero elements at the top, right, you have X3 as YT. Okay, so remember that order: X1, X2, X3. In our case, X1 is Y. If I go back, X1 is Y, right? So you would have expected to get X1. But you can arrange these equations upside down, right? X3 goes to the top, X1 goes to the bottom. Same system. So in here, it's like that, what you call canonical form. So in that case, you get X3 actually as your response, YT. Okay, don't bother too much about it. All right. Now this is the result, right? If you use the Kalman filter, right, in the simulation, you generate your this black dash line as YT. This is the true response. You can barely see it over here, black dash line. That is the true response, right? And then you connect the sensor and you add the sensor noise. Then you read it as Y. You can see the blue one is the noisy response. Noisy response. Can you see that? Now, if there was no such thing called Kalman filter, you would have fed back the blue noisy response as your feedback signal. But now you bring in the Kalman filter, it estimates the true response as red line. You can see the red line over here, right? Now you have a choice to make whether you want to feed back the Kalman filter estimate or the sensor reading, blue one or red one. What do you think? Which one of these two signals uh, is more appropriate to be used as the feedback signal? Of course, it is the red one, because the red signal is very, very close to the true response, YT, whereas the blue one has some noise. So that is why a lot of people use Kalman filters to estimate the responses. Actually, what they do is they estimate state variables and then they combine state variables together to generate the response. And then they feed back the Kalman filter estimate to the feedback control system. Is everything clear up to now? Now here you can see the plant with the Kalman filter, right? Same plant. Now you are familiar with the plant, PID controller, anti-wind up, everything is there. And now we have the Kalman filter over here. So we have connected the sensor output control signal to the Kalman filter, and we get the output of the Kalman filter, and this is y hat, the estimate or the response, and we feed back that to the plant. Of course, over here I have a switch. If I want to use the Kalman filter estimate, I can select it. If I want to use the noisy response, I can put that as well. All what I need to do is to check this value. If I want to have a noisy response as my feedback, right, I put number 1 here, 1 for sensor feedback. When I put 0 here, I select the Kalman filter estimate as my feedback. So for education purpose, you can do that. You set these numbers. You have the Simulink block. I did not ask you to build your own Simulink model because that would be too much here. It will be an obstacle for education, learning process, right? So therefore, I gave you this model. You can play with it, right? And see what you get. This will be really good learning curve. And after that, you will be able to draw your own Simulink block with Kalman filters, anti-wind up, etc. Okay, so if you feed back the noisy measurements, say you don't know about Kalman filter, you don't want to work with Kalman filter, you think it's a difficult thing, problematic, you decide, okay, I will anyway go with sensor feedback, right? And this is what you get, right? So you can see the control signals are noisy, lot of anti-wind up, kicking, right, all over the place. And here you can see the control signals again, PID, right? A lot of saturation of the actuator. But if you look at the response, you will not notice a huge amount of noise, okay? Because all these things are firefighting inside the control system, not visible sometimes to the outside world, right? So you will get something like this. You can see the actual response. The amber curve is actually staying below the reference for some time, and then at the end it gets to the actual value. You can see some deviation. If I get this kind of result, I would not be happy about it. Okay, if you can look at the actual the ideal response. Okay, we may not be able to get the ideal response, but we should be able to get something close to ideal response. But this particular uh, actual response is not close enough to be ideal, right, to the ideal response. So generally, it's not a satisfactory result. So if you put the Kalman filter in place, this is the result you get. Now see, how peaceful the system is, very quiet system, very gentle system, and you can see uh, the response, actual response with the Kalman filter, getting somewhat close to the ideal response. Okay, so I'm now pedaling back and forth for you to understand the difference. Without Kalman filter, with Kalman filter, without Kalman filter, with Kalman filter, without Kalman filter, with Kalman. So if you pay attention to the response over here, pay attention to the left top graph, you will see the improvement. With, without, with, without, with, without. Can you see that? All right. So let's take a little break here, about 5 minutes. All right. So this is the MATLAB code that I have given you. I can explain briefly different parts of it. You can see over here the saturation limit of the actuator. I have set it to 3 and -3. And this is the sampling interval, 50 milliseconds. This is the total simulation duration, about 20 seconds. And this is the timeline. Okay, you know all these things. And this is my reference signal, right? I first initialize it with zeros, all zeros. But then I put certain values, 1 and -1, to make it like a step signal. Okay, positive going and negative going. This is basically what you have seen over here. If I pedal back, you can see that positive going part here and the negative going part here. So this is my reference signal. Okay. Then I declare my transfer function over here. Right. This is the transfer function. Oh, you can change it if you want, right? But make sure you run this one. CS, this is the controller using PID tune command in MATLAB. You give the transfer function to it and generate the PID. And this is the cutoff 10 Hertz. And you generate the feedback control system, right? Using the open loop GS already given over here. And you do the linear simulation, LSIM, of the feedback control system for the given reference over the given time interval. Okay, and call it Y1. This is the ideal response. Ideal response. Okay, right. So here you can see the Kalman filter, where how Kalman filter comes in, right? So you need to give R, that is the sensor noise covariance. You need to look at the sensor data sheet, and the genuine manufacturers of the sensors, they test the signal of the sensor against a standard control signal, test signal, and find out the noise level, and they provide that one. This is the process noise covariance. I have put a Q over here, very small value, assuming that I have taken most of the system dynamics properly modeled. And then what comes is the numerator denominator identification of the transfer function using TF data command. And then I generate the transfer function, rather state space model using transfer function, and use TF2SS command for that. Okay. Then I open the Simulink block, PID1 KFSIM, and I simulate that. Okay. All right. So study a bit about this code and the Simulink block. When you run, you might run into problems also, right? For example, the Simulink block here, what I've given you on the model is on 2022A version. I think it's 10.4 something, right? But if you have an older version, it might give you a warning or an error, but it'll tell you what you need to do. You have to open the Simulink block in that version and then save it on a different version, and then you can put it back in the folder and can run it. Okay, so you can do all kinds of things. All right. So all the best for your tests here with the codes. All right. Please make sure you spend decent amount of time with these MATLAB codes. Finally, the summary. So I have these 1, 2, 3, 4, 5, 6 bullets to summarize everything about the PID and noise and the Kalman filter, right? If you understand all these 6 bullets and the details, you are done, right? The first one here, PID control is very intuitive controller that could be tuned for almost any plant. You don't need to have any knowledge about the system dynamics. You need to know the response, the rise time, overshoot, etc., and how these gains affect them, whether in the positive manner or the negative manner, and then you can tune it. Okay. Second bullet, PID tuning procedures are well documented. You don't have to generate anything on your own, right? You just have to follow the procedures. The association between the PID gains, KP, KI, and KD, and the time response attributes like rise time, settling time, overshoot are well established. So if you want to have a particular time response, you can figure out, okay, whether you need to increase or decrease these gains. Integral control needs to be clamped when the actuator is saturated. Okay, clamp in the sense the anti-wind up kicking, right? You stop integration for a particular duration to avoid integrator wind up. Need to know that. Okay, the derivative control needs low pass filtering before differentiation. That's very important. And decontrol is more efficiently implemented as a feedback loop. So we don't usually differentiate the error signal and multiply with the gain. But what we do is this one. We implement it as a feedback, small feedback entity, where FC is the cutoff frequency is in the forward path and integrator 1 is in the feedback path. So that is a computationally very effective way of implementing the derivative control. Last bullet, due to sensor noise, proportional control signal also becomes noisy, right? Because the noise. A Kalman filter could be used to estimate the true response, that is Y hat, and use that estimate for feedback rather than feeding the noisy sensor measurement Y. Okay. Do not feedback the sensor measurement directly and send it through the Kalman filter and get the estimate of the Kalman filter and feed it back. Sometimes or often you do the other way. Don't use Kalman filter, right? You feedback the sensor noise. Most of your projects you do like that. It works because most of the sensors are good sensors. It doesn't have a lot of noise. But if you put a Kalman filter and refine it, it will make things better always. All right, so that is the summary. Any questions, please, quickly, before we start our next chapter? You can unmute and speak. Is everything clear?